Mazzucco comes to us from branch 32, okay? And that's a big branch, Tony. Yeah, 32. Branch 32, and I think they have, 170 members? Yeah, and you guys meet here. That's really good. Tony's a really interesting guy. We've gotten to know him here today and just kind of reading his bio. He spent 35 years at Lockheed Martin on various space projects. He said he could tell us about a few of them, but he had to kill us afterwards, so we won't do that. But he enjoys, his other hobbies are golfing, hiking, pickleball. He also is very active in the community. He's involved with his church and has volunteer time in food pantries, grief sharing, and also he likes giving back to his community as a tutor. So he tutors students, grade school, middle school, in math and science. So with that, we're very lucky to have Tony here. I want to thank you, Tony, for coming. A warm welcome for Tony Mazzucco.
Well, thank you very much for having me. I really enjoy this subject. I actually never worked on the James Webb Telescope, which you go, why are you bothering being up here? Well, you've seen one $10 billion satellite. You've seen them all, right? So let's see if I can get this set. The tricky part here, right? We got a complicated satellite, but can we actually get our Zoom picture shared with you here? Okay, that looks like that worked. Is there a way to make it bigger? That's my sense of humor over here. I won't repeat what you just said, but is there a way to enlarge this further? You tell me. I've got it on full screen here, but this is really going to be an eye test for you. So hopefully today I'm going to take you on a little journey. Hopefully you'll enjoy this. My goal is to keep 90% of you awake. The rest of you, enjoy a nice little relaxing rest. But many of you, I'm assuming, have heard of the James Webb, but some of you haven't. So I'd like to walk through kind of what is a James Webb? Who is a James Webb? Where is a James Webb? And why is a James Webb? What is it all about? And for something as complicated as this, I often try to figure out, well, where should we begin? And so where I like to begin, well, there we go. I like to begin in the beginning. Why don't we start in the beginning? And in the beginning, someone said, let there be light. And there was light. Okay. Well, I'm having trouble with the clicker here. I don't know why it's taking so long. Maybe it's just a delay. Okay. And there was light. And that light is still traveling today at 186,000 miles a second. And that is really kind of the crux of what we're going to be talking about today, the fact that light takes a certain amount of time to travel. And so the James Webb Telescope in itself, while looking back at far, far away objects, is actually looking back in time quite a bit. So far back that we're looking at close to the beginning of the universe, when shortly after the Big Bang. So just to kind of make sure you understand that simple concept, we all know we have the sun in our sky. That light takes 8 minutes to get just 93 million miles to us. So we're looking at the sun 8 minutes ago. And if we were to take something like a nice telescope and go away from the Earth 1 light year, and 1 light year is not a unit of time, it's a unit of distance. It's the distance that light travels in a year. So if you were 1 light year away, look back at the Earth with a powerful enough telescope, you'd see the Earth a year ago. If you went 100 light years away, look back, you'd see the Earth 100 years ago. And if you went 1,000,000 light years away from the Earth and you had a powerful enough telescope, you could see the Earth 1,000,000 years ago. So that's the concept. We're looking back at not only objects that are far away, but that were a long time ago. So hundreds of millions, including billions of years ago. So just wanted to keep that in mind. We're looking not only at objects far away, but a long time ago. Might have to just the old-fashioned way here. Okay. So before we begin, I've got a little third grade chart up here for us that we can walk through. Just want to make sure you follow some of the terminology we're going to use. So I call this cosmic terminology. You may not be able to see the title up top. But the first item up there, a planet. I think you all know what a planet is. It's an object that orbits a star. And in our case, our solar system, we're orbiting our sun. The next item, a star. If you remember The Lion King, it's a large ball of gas, and everything's about gas in that movie. So the star is a large, luminous, bright object, creates its own light. What did I do? Did I do something? I don't know. So it looks like it's still on my screen. Oh, there we go. So a star, again, a large object, it's held together on its own gravity, generates light. The next level up, a solar system. You've heard of that. So it's the star and all the objects that are orbiting around it. So including planets, including asteroids, including anything, dust, debris that is orbiting that star. That whole system is called a solar system. I think you're all familiar with that. The next level up, the whole collection of all these solar systems, lots of them, billions of them, is called a galaxy. You've probably heard of that term. Does anyone here know what the name of our galaxy is that we live in? Did you say that, sir? I heard you. You were the first one to say it. Congratulations. You get your nice Milky Way. So yes. So the Milky Way, we're going to talk about our Milky Way. We're going to talk about a few other galaxies that are not too far away. The next item is a nebula. Maybe you've heard of the term nebula. We're going to spend a lot of time on nebulas today. They're very beautiful. If you're a Star Trek fan, you remember whenever time the Enterprise would go into a nebula, they would have all sorts of problems, communication, havoc, all sorts of things. Well, the nebula is a large, massive amount of dust, debris, gas that isn't really formed into anything yet. It's in the process of either being the result of a star that has exploded and decaying or the birthplace of new stars. And I just want to kind of share that our universe is a really great recycling center. So what's happened over time is that stars will be born, they'll live, they will die, they will explode, and as time goes on, they create heavier and heavier elements. So in the earlier universe, just the lighter elements were there, the hydrogens, the heliums, and every time they're recycled, they get more and more elements like we have today, all the way up to our periodic table. If you fell asleep through chemistry, remember all those elements, those are only created through recycling of stars and star material and matter as things cool over time. And then finally, the universe itself, which is all of that contained together, which amounts to about 2, which each containing about 100 billion stars each. So it's a pretty massive universe. We'll talk a little bit about that as well. I'm just going to use this button here, make sure. It says signed out. Okay, all right. So you can still see this. I know, again, I'm testing your eyesight. I can barely see it from here. Okay, so James Webb. What is James Webb? So it is a space telescope. Stands for the James Webb Space Telescope, right in the title. How hard is that to remember? But it works primarily in infrared light. So Hubble and our eyes primarily see invisible wavelengths. We're going to talk about why James Webb is in the infrared spectrum and why that's important coming up. So NASA, along with the Canadian Space Agency and Europeans, work together on this. It's a collaborative effort. In fact, all the data that's collected from this is shared across the entire planet. So anybody that wants to can have access to the data it's collecting and work together as scientists. It was launched, finally. It was originally supposed to launch in 2007, had a few delays, but finally, on Christmas Day of 2021, it was launched. It took 30 days to get to its final orbit. And I'll show you where that is. It's not actually orbiting the Earth like some of the other satellites. We'll show you it's got a very interesting orbit. And it took 6 months for it to be deployed, calibrated, checked out, and ready to take the beautiful images we're going to show today. So about middle of 2022 was when the first real images started being produced. It's considered the successor to the Hubble. It kind of works in tandem with it. It's not to replace the Hubble. Again, it's working in a totally different set of wavelengths of light. And who is it named for? James Webb. Who is James Webb? Everyone knows. No, maybe none of you knew. He was the administrator of NASA during our major space program, so Gemini, Mercury, and the Apollo missions. So it was named in his honor. So the mission itself of James Webb is, well, I'm going to tell you a little bit about its orbit now. It is orbiting the sun along with the Earth about 1 million miles away from our Earth. its goal is to look back at some of the earliest stages of the development of the universe, about 100 million years. That sounds like a long time, but it's very young stages after the Big Bang. And the best theories today say that the universe was created all at once. Time, matter, and space all were created about 13 billion years ago, and it's been expanding into what we don't know, but it's been expanding ever since. It's going to be looking at how the universe has evolved over time, and it's going to also look for potential signs of habitable planets in various parts of our universe. And it's also able to look at some of the planets within our own solar system, and I'll hopefully show you some of those as we move along. So along with being engineers that understand optics, thermal, all of the various aspects of I'm trying to think, space systems. The word I'm looking for isn't coming to me. Say it again? Aerospace was the simple word I was looking for. I worked in aerospace only 35 years yet. Poof, it's gone. Aerospace, they had to be experts in origami because you have to be able to take this telescope that's roughly the size of this room, literally, it's 3 stories high, but it would fill this room end to end. You have to be able to fold that up into something that can be launched. And then, when the time it's launched, it takes 30 minutes before it's separated, sent on its way, and then it is on its way for about 30 days to get to that final orbit. But during that time, it takes about 14 days to open everything up properly, in proper order, one thing at a time. About 300 actuations had to take place, any of which didn't work. We would not have a fully deployed and successful telescope. We'll talk about some of the parts of that coming up. So the telescope itself may not look like a telescope you're used to. It doesn't have that barrel or tube on it. And so what it has instead is this giant sun shield that's primarily made out of thermal blankets, kind of like the same thing your Mylar balloons are made out of. A metallized sheets of plastic, many layers, and this is designed to keep both light and heat off of the telescope. So infrared, if you aren't aware, that wavelength is something our eyes can't see, but it's very much the same thing as heat. So warmth, things that are warm, generate light, we'll call it, in the infrared spectrum. So this telescope itself, made of 18 segments that are all controlled individually to form one big complete mirror. It's made out of a metal called beryllium that can handle the cold temperatures. It's coated in gold, and the reason for gold is it's the best reflector of infrared light. So most of us are used to mirrors being silver because that's best for visible light. So gold is best for reflecting infrared light. Light would come in, bounce off of this giant primary mirror, off of a secondary, back through the center hole, and there's a set of 4 instruments, we'll kind of cover them, or cameras behind that. All of this has to be maintained to be outside of external light sources and also very, very cold. Down on the bottom side are the other important pieces that include the solar panel for collecting energy, the spacecraft bus, which controls the attitude. So this whole telescope, as big as this room, I got my little paper doll. You're all able to print one of these out at home as well. It basically has to keep one side always facing towards the sun, and when it moves the entire telescope. So the attitude control system points all of this at once. It's not just trying to rotate just the telescope part on top. The whole thing, the size of this room, is going to rotate and move, keeping the bottom side towards the sun, the telescope side away from the sun. But it has freedom to move certain angles to look at various parts of the sky. So comparison to Hubble, while the James Webb is quite a bit larger than the Hubble, it's quite a bit lighter also because a majority of it doesn't have that barrel. It's got mostly this huge sun shield that's made, as I mentioned, just kind of thermal blankets, very lightweight material. So it weighs about 11,000 pounds less than the Hubble. Both of these were designed to last really 5 to 10 years. As you know, the Hubble's been up there since 1990. It's going to come up in 36 years of mission. It's still going strong. And right now, the estimate is that while this was designed for 5 to 10 years, its life limiter was really the propellant that's on board to keep it in its orbit that it needs to maintain. I'll show you that coming up. But because the launch put it very precisely heading for that location it needed to finally be, they didn't need to use very much propellant from the spacecraft, much at all. So they estimate now that you have at least 20 or more years, which is a good deal because it cost only a mere $10 billion to put together. Now that sounds like a lot, but the Hubble was $1.5 billion, and they're pretty comparable in today's versus 1990 dollars. So comparing this, what am I doing? Okay. Comparing the size of the mirrors, you can see a human being here. Hubble's got an 8-foot glass mirror coated with silver. And we have this 18-segmented mirror that's 21 foot tall. And with that large amount of collection area, it can collect a lot more light than Hubble could. So it can see objects that are 10 to 100 times fainter than what Hubble could do. So an incredible change from what we had before. The 4 instruments, not going to go into too much detail for you, but I wanted to explain there are 4, and the 2 on the bottom here are the workhorses. One that's called NIRCam, which is the near-infrared camera. That's the wavelength of light it collects in. And then MIRI, which is the mid-infrared, and they both serve different purposes. But along with that, I want to explain a couple other important things that go along with the cameras. One of them are something called spectrographs, and maybe you've heard of that. Kind of like the way a prism works to break up visible light into the rainbow, you can slice up infrared light into its various spectra also. And that's important in identifying the chemical properties or getting signatures of what the temperatures, what the object they're looking at, what it's actually made of. So if you remember your Bunsen burner back in high school chemistry, and you stick it into the fire and it would glow a certain color, and you figure out, okay, it's orange, that means it's this, or if it's green, it's this. Kind of the same thing. They're able to fingerprint in infrared light what the compounds are that they're seeing by slicing up the light into smaller wavelengths. And the other thing these carry are something called coronagraphs. You may never heard of those either, or maybe you have. But the fact that they're also trying to find what we're going to call exoplanets. We talked about what a planet is, you guys all know that. But an exoplanet is any planet outside of our solar system. So it's out orbiting another star. In order to see those tiny, tiny faint objects, the star itself is going to be too bright for that camera to see. It's going to be drowning it out. It's like trying to see a firefly when you're looking at a stadium light right next to it. You wouldn't be able to see that firefly. So a coronagraph is a device, mechanical, that can be placed over the top of the star in the field of view of what the camera's looking at, so it can block out that relatively bright light and see anything dim around it. And I'll show you a few examples today. So just a quick reminder that we have to try to keep this telescope side very, very cold. And when we say very cold, if you're familiar with the term absolute zero or 0 Kelvin, which is minus 460 degrees roughly, we have to get this down to just 6 Kelvin or minus 449 Fahrenheit. And that's the reason is that any warmth from any of the electronics, any of the camera itself is going to interfere with itself. So they got to keep the camera and everything back there really, really cold, and it has to survive those temperatures. So the hot side, so to speak, not super hot, it's in the sun all the time, but it's, I don't know if you can see these tiny numbers, but 55 to 89 degrees. So kind of room temperature, the parts that are in the sun all the time. So the orbit, we mentioned it's 1 million miles away from Earth. Up in the top, showing you the Hubble orbits about 300 miles off the Earth's surface. Goes around about every 90 minutes or so. But where do we put James Webb? It is out 1 million miles away from the Earth. It's at a place called a Lagrange point. Anybody know the famous French physicist, astronomer Lagrange? You cousins? No. So, but you've heard of him. So he helped identify these, I'll call them gravity wells, or places where there's gravity equilibrium, where you can place something and it'll tend to stay there. So you can imagine between, this is a kind of the top view of the Earth's orbit going around the sun. you can imagine a point between the Earth and the sun where you could put something and the gravity forces would even out and it would kind of stay there. Well, there's actually points behind the Earth and in front and all the way on the other side of the sun that kind of do the same thing, where the gravity forces all are equal. So what happens is they put it out here so it's way away from the warm sources like the sun, and the Earth's a very warm object too. So it's away from that, and now it will stay with the Earth as it goes around on a yearly basis. It's going to orbit this L2 point, and it's going to stay there, orbiting essentially in an imaginary place where the gravity well, all the forces equal zero. So here's a quick little animation of that. So as the Earth's going around the sun, the James Webb is orbiting. It's actually going in an orbit called a halo orbit around this imaginary point, and it's staying with the Earth. So it takes 365 days to orbit the sun, staying with the Earth the entire time, 1 million miles away from us. So now to get into the wavelengths of light. So why infrared? This is what we want to talk a little bit about here. So here's the spectrum. We've got the higher frequency light here all the way down to the lowest, larger wavelengths and lower frequencies where radio waves are. So Hubble operates up here in the visible light primarily. It can see a little bit into the infrared, and our James Webb here is going to operate totally in infrared. So why is infrared important? Why is that even a thing? I'll give you 3 reasons. One, first of all, light is scattered by the dust in space. And you think, well, isn't space vacuum? Mostly, but there's a lot of stuff out there between here and other galaxies that consider dust and gas. And the light, visible light, is scattered quite a bit by that. But infrared light, the wavelength can pass through that. So that's the first thing. It can see through the dust of space. The second is it can see faint warm objects that don't have to be illuminated by a light source. So planets themselves generally don't emit their own light. They just reflect their sun's light. So this can see warm objects without having to be illuminated by its star. And this last one, which is probably the most important, and many of you have probably heard this term, is due to something called redshift. Has anyone heard of that term? Does everyone know what it means? Well, I'm going to try to give you, again, the third grader version of it. So something called Doppler shift. Who's heard of Doppler shift? Okay, so the same people. So I'm going to give you an example in sound. So you've probably heard as a siren approaches you, not only is it getting louder, but the pitch or frequency is increasing as it's coming towards you. And as it leaves, obviously the sound goes down, but the pitch also gets deeper. And that's because the speed of sound is constant in air, and as something's moving towards you, it's actually compressing the waves and forcing the frequency to be higher. And as it goes away from you, it's stretching the waves and causing the frequency to drop. Very similar in light. So light has a constant speed of 180,000 miles per second. And as something's moving towards us rapidly, it's going to compress the light waves and force it to shift into the blue, invisible sense. It's going to force it to shift up into the blue light. And things that are moving away from us, it's going to stretch the light and force it into the red or even infrared. So what's happened is objects that are the farthest away from us are moving the fastest away from us, and they have shifted in light wavelengths so far that we can't even see them with visible light. So if the Hubble was 10 times the size it was, it still couldn't see these objects because the wavelength that it can detect is no longer there. It is shifted into infrared. So that's the main reason. Objects that are far, far away from us, moving faster away from us, the light is shifted into what we call the red or infrared spectrum. So that's the term redshift. I hope that kind of made sense for you. So here's an example of Hubble images. And before you leave here today, you're going to be experts in being able to tell the difference between a Hubble and a James Webb picture, by the way. So pay careful attention here. So this is a part of the Eagle Nebula known as the Pillars of Creation. You've probably seen cool calendars with this. This is a very popular, beautiful image. Kind of looks like a hand. Here it is, Hubble taking it with its visible sensor, and here's Hubble taking it with its infrared. So you can see that it can see infrared helps go through the dust of space, so to speak, much easier. Also, I don't know if you can see from where you're sitting. I know this is kind of tiny, but can you see these bright points? They have these light spikes coming at them. They're called diffraction spikes, diffraction patterns. And for Hubble, you'll see that it's in the shape of a cross or a plus sign or an X. So 4 spikes coming off of it. And that's because of the way the struts are designed and point sources, the way they refract around things in front of the actual mirror. It's going to cause these patterns that create these diffraction spikes. So you're going to see a 4-sided object in all of Hubble's pictures when you're looking at a bright point object. You're going to see something different when we get to James Webb. So here's, you may not be able to see this from where you're sitting also, but we'll have some that are enlarged later. So here's the same pillars of creation from James Webb. And this is using the near cam, the near infrared, and the MIRI, the mid infrared. And you can see just already, there's already difference just in those 2 wavelengths. I also want to point out that these are colorized intentionally because infrared light we don't see. They're getting, basically grayscale, but they've colorized them to look like what Hubble would see, or natural visible, so that our eyes make sense of it. So this is what it would look like this is what it was through James Webb, and they can combine the images together and form this beautiful work of art that almost looks like, I'd say like an artist's rendition of it, but this is an actual photo, and maybe you can see it from where you're sitting, but this point source here, the point bright lights, it's actually got a 6-sided set of spikes. So, and there's really another small set that makes it 8, but generally you'll see a 6-sided because of the shape of the mirror and the fact that it's got 6 sides and it's got 3 struts. Those together are going to keep forming 6-sided spikes in all of the James Webb. So if you're looking to say, am I looking at a Hubble picture? It should have 4. If I'm looking at James Webb, it should have 6 almost bright star items in the picture. So just to give you a perspective, this is the entire Eagle Nebula, and it's about 55 light years across. So it takes 55 years for the light to cross from one side of this, which is a relatively small nebula, only 55 years for the light to move from one side. And this is in our backyard. It's only 7,000 light years away from Earth, so relatively close to us. So just to see where that one picture was taken, down in the middle there. So we'll show you stuff that's much, much older as we go through. Here's an example comparing James Webb on the left to Hubble. You can see quite a bit of difference and a lot of different information. The title up top there is the Phantom Galaxy. I'll try to read you the titles because it seemed to be off the top of the screen a little bit. This is a little further away, still kind of in our backyard, 32 million light years away from Earth. And it's 31,000 light years across. So a galaxy is typically something more that size, 31,000 years for light to pass from one side of a galaxy to another. Here's an example of, it's called the Carina Nebula. I'm trying to read you the top again. Just not only can James Webb see a lot better resolution, but it can see, it takes a lot bigger area at a time. So just an example of what Hubble is overlaid on top of this James Webb, and I'm going to remove the Hubble so you can kind of see how much the resolution has improved. I'm just going to go back and forth a couple times so you can kind of see how much more detail is available through James Webb. Here you might be able to see the 6-sided spike and these bright stars, these point sources in the image. So you should be seeing a lot more of those as we go along. Okay, so the title there says, how much can James Webb do? I'm sorry, which is a little too high. I don't know why that is. Yep, that's all. We're done. So how much of the sky can this see at a given time? We talked about the fact that it's restricted in where it can look because of the sun, and the Earth has to stay away from that. So it can see about a 50-degree swath, which is about 39% of the night sky. It can see at a point in time. But over a 6-month period, as it's orbiting the sun from one side to the other, it has access to the entire night sky after about 6 months total. So they have to be very selective in what they want it to image on any particular day, knowing that I only have 6 months to see until I get to see that object again as I come around. Beautiful. Thank you, sir. There we go. So it can see a kind of it takes about 6 months before it has the ability to see, have access to everything. And what if we wanted to map the entire night sky with this telescope? Well, it looks through something that we call similar to a soda straw. It's seeing something very small at any point in time, and what it can look at, about 0.04 degrees. So from Earth, when we're looking at the moon, that's a half a degree. So this is less than the tenth of the moon that we would look at night, is all it can see at one point in time. And if we were to try to have it map the entire night sky, which is about 41,000 square degrees, it would take a mere 26 million images. Okay, can it do that? Well, given that it takes about 12 hours of staring with the camera lens and the aperture open, it can hold precision pointing for that easily. It's very accurate in where it points. But a typical image might take 12 hours to collect because of how dim and how much light it has to collect from so far away. So if it was going to collect a 12-hour image, it would only take 36,000 years to collect the night sky. And if we even took it at some of its fastest collection rates of 2 hours, it would still take 6,000. So clearly that's not its mission. It's not to map the entire sky. It works in concert with other telescopes on the ground and in space to decide what's the most important to collect. So how is James Webb doing? It's been up there now, coming up on, it'll be 4 years. Its health is excellent overall, doing very, very well. All of those deployments did great. And as we mentioned, the orbit that it got to didn't require the use of hardly any of the propellant. So it's still got enough fuel to last 20 or more years. It has had the primary mirror damaged, though, slightly. So there's things called micrometeoroids, which are smaller than a grain of sand, more like a dust particle, that are out there. And when this is flying through space, it slams into those, and it can damage that metal mirror. So I'll show you a quick picture of that coming up. But it was mostly correctable, and it's still way outperforming its requirements. And they've also, to avoid slamming into things like that, they've tried to minimize how much time the primary mirror is facing. So this can fly through space at different angles, try to minimize how much time the primary mirror is facing in the direction of the orbital path. So they try to point it behind, so it's just to protect that mirror a little more. Also, it's got some minor issues with the MIRI sensor, some of those things that I talked about that divide up the light into multiple individual frequencies or wavelengths. One of the wheels that provide that looks like it's a little slower than normal. It's sticky, but so they just have to account for that when they take changing between those different wavelengths they want to look at. So here is a picture of a selfie from looking through its own mirror with a camera that can see its own mirror. This is what it looked like when it was first put together and pristine. Here you can see this bright spot is where that micrometeorite struck. Caused a little bit of an imperfection there, but they're able to rotate each of these segments, these 18 segments, either rotation, tilt, or even in and out, so that they can try to minimize how much that impact is affecting the overall big mirror performance. So it's doing well, but they're now trying to minimize smacking into any more of those potential particles out there. So what has it found? What are the things that have been big findings since it's been launched? I'm going to show you some pretty pictures, which is really why you're here, but what else has it discovered? So you might have heard this term called the crisis in cosmology. Are our models all wrong that we've been predicting the beginnings of the universe, how we're expanding, the expansion rates, all of that? Everything seems to be turned on its head. People are panicking. Dogs are sleeping with cats. It's a crazy world. But one of the things, what's called the Hubble constant, the expansion rate of the universe, has been something that they've had two models that never quite agreed. This is actually helping them get those particular models to agree on how the rate of our expansion of our universe, and also does that change over time? And it looks like the rate of expansion has been changing. Something we're calling impossible galaxies. So in the earliest days of the universe, when everything was hot, just starting to cool down, they didn't expect a lot of mature galaxies to have formed until much, much later. But they're seeing things that seem way bigger and way brighter than they would have expected based on their models. So I'm going to talk about that coming up. And then there's also this fancy word called protoplanetary disk. So the earliest formations of a solar system involve kind of a swirling set of masses that eventually will form into a star in the center and then objects that solidify into either gas planets or solid planets orbiting around it. So they're finding some of those earliest protoplanetary disks seem to be lasting much longer than they would have expected. I'll show you some examples of that. They're also seeing black holes, which we're learning more and more about, appearing way, way in the earliest set of universe also. And they're kind of, that's interesting. We didn't know that would form that early also. But some of the models are saying, well, yes, now in the earliest stages, everything was more densely packed together before it expanded to the state we're at now. So maybe it makes sense there was more material there that would have been pulled together by gravity and formed much bigger black holes back in the earliest stages than we thought. Also, it's been able to look at potential habitable exoplanets, seeing organic hydrocarbons out in some of the potential, out in exoplanets that could be potentially habitable, similar to Earth. And just some kind of interesting thing, within the nebula, usually gravity kind of takes over and everything has a place to go. They're finding these wandering binary pairs that don't seem to have a direction or being pulled in by anything else. They're just wandering aimlessly in those nebula. So on to this one item of the crisis in cosmology. Why are we seeing objects or what look like galaxies that are way more mature, way more formed than we ever expected? And they call these things little red dots. So they're not just one, but several of them they keep finding that in the oldest time look like they're way brighter and way bigger than they imagined. So the more they thought about it, and the discovery of kind of the black holes in the earliest days, their conclusion, at least of the week, we'll see what happens next week, is that these aren't really massive galaxies with lots of stars, but what they are is a black hole that's pulling all the matter around it in at such high rates of speed that it's creating friction that's causing all of this matter to glow brightly. So it's just the high rates of speed and the force is being pulled in on all this matter. So they're not necessarily mature stars generating their own light, but they are all the matter getting sucked into the black hole actually glowing. And that's what their current theory is on that. And here's evidence of black holes that seem to be as old as only 470 million years after the Big Bang. James Webb is working in concert with another telescope called Chandra, which works in the X-ray spectrum, and that helps them understand black holes in that wavelength a lot better. And they are finding black holes that seem to be existing as old as just a few 100 million years after the Big Bang. So that's kind of helping their theory hold together that black holes may be the cause for these what appear to be giant galaxies that shouldn't exist yet based on their models. They're also seeing these protoplanetary disks. Now, I know you can't see these at all because I can't even standing right next to it. Inside of these little yellow circles are these areas that are the earliest formations of early planetary disks that really are just made with hydrogen, helium, all of the very lowest level elements that seem to be lasting much longer than they imagined. And so this is helping them think, okay, so planets way back then could have taken their time to form, but they already had these starting points in the earliest times. But they are very lightweight, and they have not been recycled yet. So one of the things we're going to see on this little journey together is that the universe isn't uniformly recycling. There's different neighborhoods that recycle much better than others, and others that haven't even started recycling yet. They're still the younger versions. They have not gone through the same evolution as other sections. So looking at these kinds of cases, they can kind of understand the whole evolutionary path by looking at different sections of the universe that have different stages of evolution of that recycling going on. So how do they see exoplanets? They can barely see stars far away. How are we seeing tiny little planets orbiting those things? So there's two ways they're looking to find exoplanets. One is indirect and one is direct. So indirect, what does that mean? One is they can look at a star and see that it wobbles. And that indicates there's some other mass, like a planet around it, that's actually tugging on it. Maybe you knew this already, but especially because of Jupiter, our sun wobbles quite a bit. And the center of our solar system moves around quite a bit as our planets tug on the sun as it goes around. So that's the same thing. They can stare at a star and start to see its wobble, and what its period is will give them an indication of planets orbiting that. The other way is when a planet happens to pass in front of a star, it's going to dim that star ever so slightly, but enough that's detectable, and they can tell, okay, something passed in front of it. Maybe more than one thing will pass in front of it. One of the issues with that is James Webb can't sit there and stare forever at a star. So, for example, the Earth, to detect the Earth, if the Earth happens to pass, how long does it take for the Earth to go around? A year. So Earth's transit of the sun is only going to be once a year. So these are planets that they're seeing that are actually whizzing around their sun pretty quickly. And so they're very close. They're generally way too hot to be habitable, at least by our life form. So, but they're getting a start at how to see whether a planet has exoplanets around them. And for now, they're mostly the ones that have a very fairly quick return rate, coming zipping around. They also, when they look at these planets, when they pass in front of the sun, their star, the light that's blocked isn't blocked uniformly. It's blocked different wavelengths differently. So they can kind of see what the atmosphere of that planet is made of, believe it or not, by looking at what light's transmitting through there and what light's being blocked. So that is helping them understand the composition chemically of certain atmospheres. Now directly, as I mentioned, we had this coronagraph where you can block the bright star and then actually be able to see without being drowning out the image. You can see planets nearby, but that's limited to certain distances from that star as well. So here's a quick little animation of what we're talking about. As a planet passes in front of the sun, there's going to be a little dip. And again, it's minor, but it's enough that they can easily detect that and then start getting the frequency and period of certain planets. And some they've discovered have multiple planets orbiting them. But again, they're in close and they're whizzing around pretty fast. Now, here's the pictures you've all been waiting for. No, but this is what the scientists really care about. So this is what they spend most of their time looking at while we want to see those beautiful pictures. So the spectrum of light, due to the chopping up all of the different wavelengths, this is what the image looks like for them of a particular planet. They've named it exoplanet K2-18b, very creative, but it's around the star they named K2, and it's planet 18b. They call this a Haitian planet, and that's because they believe it has a hydrogen atmosphere, but maybe a water ocean. And they can see that through the spectrum of what's transmitting through the atmosphere as they see it go by. So I'm not sure that's a very healthy place to live. I'm pretty sure there's no smokers on this planet if the atmosphere is all hydrogen. But they're starting to see this kind of planets that are, understanding all the different kinds of exoplanets, much different than what we have in our solar system. Here's another case where they've discovered some organic molecules, so some kind of hydrocarbons. In this case, they're seeing ethanol and formic acids and methane. But again, that's what it looks like to us, what we want to see. This is what these scientists really like to look at, is that spectra again of what light is being blocked and what light is transmitted, so they can tell what the chemical makeup of that object is. So they spend more time looking at this. Again, I'm going to show you more pretty pictures. That's what you really wanted to see anyway. But before I do, here's what an Earth-like place that would have a rocky planet, not necessarily our atmosphere, but things that indicate there was an actual rocky planet formed. This is what the spectrum would look like, including things like water, carbon dioxide, hydrogen cyanide, and acetylene. Again, a lot of interesting, heavier chemicals being seen over time. So we have, using the coronagraph now, these are direct images the first time. And again, they're learning a little bit as they go how to really refine how to do this process. It takes a while to set up, to get the coronagraph blocking that bright star in the right place at the right time. And then they're able to use different cameras or instruments on board James Webb to see this is a particular exoplanet that they could see by direct imaging, not just by the inference that it's there or as it passes in front of the star. There's a couple more along those lines that the more they learn how to do this, the better they're getting. Here's one that looks like it's one of the colder ones. It's further away, not so close in, yet its orbit is still potentially quick, but they didn't need to worry about that by catching it, by blocking the star. They can go ahead and see the planet directly and start understanding its composition without worrying about it passing in front of the sun. And then I think they said this one's about the size of Jupiter. And this next one here is about the size of Saturn. And they didn't even know this one existed. This was one they looked at on a particular sun or star called TWA. And I don't know where they get these wonderful creative names all from. But by blocking this, this is one of the ones that is, again, close to the sun. It's a little warmer, but it is about the mass of Saturn. And Saturn's a massive planet, too. It's the second largest on ours compared to Jupiter. And they found, for those of you that have been looking at the Orion Nebula, maybe some of you are astronomers, can you see right there where they found the methyl cation, which is a carbon molecule found, carbon compound? Can you see it? I know you're all looking at me. No, of course not. Well, let me zoom in for you. Aha. Well, there it is, clearly right here. Zoom in. This little yellow blob, as it looks like, is one of those early protoplanetary disks that will form a sun and the planets around it, and it's already been recycled enough that it's got a heavier set of compounds that include carbon. So a ways away from being a place we might want to visit, but they're able to find these things in those early stages of development. And once again, just to remind you, you can see clearly here these bright stars, that six-sided set of spikes. So stars being formed, this is an example of what a star forming might look like, or does look like, because this is a real picture, not an artist rendition. And the star in the center here of this hourglass, this is forming with the axis here, the equator, spinning around here, and through the poles, it's jettisoning a lot of material as the star is all coming together in the mass. So typically stars are formed by objects, not objects, but a lot of matter forming and spiraling together and then condensing together through gravity. And through the poles, it's going to be emitting these bright plumes of other forms of gas. Here's another example. Again, beautiful colors as they use the actual wavelengths to map to what color Hubble or something similar we might see. Here's another one that they believe are two stars forming together. And quite a few stars, we have a star that's a single star in our solar system, but a lot of stars form binary pairs. They're orbiting around each other. A lot of centers of solar systems. Here's one that's going to be a binary pair when it's finished forming. And here's another one that's a very large, massive sun that's forming, or star. And they say that the distance across here is 8 light years. It takes 8 years just for the light from this one star to reach each other, from one side to the other. It would take light 8 years to travel. And so this, again, will be the formation of a very large star itself. Some more pretty pictures. This is called a Magellanic Cloud. Again, another fancy term, NGC 602. And this is something not too far from us, so it's not as old as a lot of the things we're talking about, yet its material properties look like they are still just the lower elements, a lot more hydrogen, helium, not a lot of the heavier elements we see. So this is an example of a case where the universe is not recycling uniformly. Some places still have some of the basic beginning building blocks of solar systems, and some have gone well beyond and recycled multiple times. Here's an example of another nebula, and the things that, beautiful set of stars in the middle here. But this area up here on the left, while as bright as it looks, they've discovered is really just reflecting light from other stars. So there's so much dust and other material in there that it's become just a reflection as opposed to generating its own light. So in some cases, they have to be aware of what's generating light, what is a star, and what's just reflecting light from nearby stars. Okay, so Perseus, we have all these constellations and different nebula that are named after the constellations. This is one where it's kind of like a nursery of new stars forming, and these are some of the tiniest stars. They call them brown dwarfs that are floating around. So very tiny, almost the size of planets. that are forming in this particular recycling nursery. They use that term to represent brand new stars being born inside of some of these nebula. I just find these pictures beautiful. Here's one they call the cosmic cliff. So now they're naming stuff some pizzazz, not just these numbers and letters. And so this is a combination of JWST with the kind of the golder, orangey color, and the purple spots are areas where Chandra, the X-ray telescope, has been able to actually detect newborn star clusters being formed. So they combine images quite a bit between multiple telescopes to get more information that way. And as far as the furthest star found to date, I'm going to point it to you right over here. It's called Arundel. And I don't know, again, depending on how your eyesight is, you might see that there looks like there's this kind of big curving streak here. And is that a blur? What caused that streak? So this is a real interesting phenomena that they're finding called gravitational lensing. And what that means is, in this image here, where this is taken from, there's an object somewhere over here that's likely a black hole that is so massive and pulling in with so much force, it's causing light to warp around it, and it actually creates a magnification lens. It's kind of hard to understand, kind of hard to believe, but light is actually being bent around it and magnifies what's behind it. So Arundel over here is probably not physically located there, but the light is being bent around and it's magnifying this. So they can back that out and figure out how far away and how old it is. So it is the farthest star seen to date, and I think it's saying it's about 28 billion light years away. So way, but this gravitational lensing is helping them discover things that are back behind these black holes that are even further away that they might not be able to see without that amplification or magnification of this lensing. So now I got some silly ones and fun ones, but this, again, back to some more creative naming. These two galaxies are called the penguin and the egg, and you might kind of guess why. These two galaxies here, this little bright one and this thing that looks more like a penguin, are about 100,000 light years apart. So they're kind of close to each other as galaxies go. And here's what it looks like with the MIRI. So just, again, they're looking at things from all wavelengths to understand a little bit more about it rather than just the one set of images. This one, if for the astronomers in the room, you may have pictures of this in your house that you've taken yourself, called the Horsehead Nebula. This was with a telescope called Euclid. This one was from Hubble, a little more resolution. And then James Webb has been able to get the finest resolution to date of the Horsehead Nebula. And this is it zoomed in compared to, I'm imagining folks that are taking pictures at home from a ground telescope might get something that looks more like this, but the resolution of this, also not having to deal with the atmosphere of Earth to look through, just phenomenal amounts of information. So not only do we see pictures of the beginnings of a new star, but also the end of life of a star. And you probably have all heard of the term novas and supernovas. As they're exploding, they're collapsing upon themselves and then releasing large amounts of material that again will eventually be recycled again into new stars. So this one's called the Wolf-Rayet star, and it's in the middle. It's giving off all of this, and it's 30 times bigger than our own sun and has already shed about 10 of our sun's worth of material as it's in the process of its slow, dying essentially. And here's another picture of another supernova that has been being watched since 1987. So in a relatively short period of time, just since 1987 to 2016, Hubble has been able to collect these pictures of this particular supernova. Again, they named it based on the year they found it, 1987. They've been watching this as it slowly is changing, but over a relatively, just a few decades here, not over millennia. They can see that now using James Webb to look at the same supernova. They're able to really dig into the heart of what's going on and the materials and what it's giving off as it's starting its process of slow decay. So they're able to learn a lot more, again, between these two. And there's a lot of coordination between a lot of the telescopes on the ground, Hubble, as I mentioned, and then they'll have James Webb look at a few things that are of high importance. In fact, I don't know if I mentioned this yet, but there's an international committee that every year gets together to decide, and they submit papers of what is that the experiment or what do we want you to look at for next year. And then they have a set of experts decide and judge what's the most valuable, given the amount of time that this telescope has to offer when it's flying through those areas. So this is another example of a reflection where during a supernova, which is giving off a lot of bright light, certain other objects are illuminated, and in this case, we're talking about a set of basically dust that are shaped by magnetic fields, they believe, in this particular region of space that have formed what looks kind of like almost like wood grain to me. And they would not really have seen this without a flash bulb, as they're calling it, with a supernova lighting it up. So they've been able to see some interesting phenomena out there of just how the dust and gas are shaped and flowed due to magnetic fields. Here's an example of two galaxies that are considered passing in the night, a near miss. They're not colliding with each other, but they're going to pass by each other. And I think you might be aware of this, but I'll share with you in a minute. Here's another example of two galaxies that did collide at high speeds and form what they call the cartwheel galaxy. So over a long period of time, this is not instantaneous, two galaxies can pass into each other, and then through gravity become one. And so this one's considered the cartwheel galaxy, looking at from two different spectra. Here's the mirroring image of it, looks a little different. But you may be aware our solar system, which this gentleman and most of you probably knew was the Milky Way, we do have another galaxy not too far from us. Is time up? Okay, we're almost done. We're almost done. We have another galaxy on its way to collide with us. And Mike, I said, you have a little more time. So it's called the Andromeda Galaxy, and it's about 4 billion years away from colliding with us. So you shouldn't lose any sleep over it. I've been told to speed up. So what we're going to do is show you a few cute pictures, galactic oddities. That set of rings, which they didn't know really what they were until they saw with James Webb, are a set of two stars, those binary pairs that are zipping around each other, spraying out dust every time they get closer, and material that have formed what look like tree rings every time they pass, and they can tell the frequency is about an 8-year cycle as they go around each other. And before that, all we saw was this much from other telescopes. There's just the two rings. So quite a bit more info. A gorgeous picture here called the starlit mountaintops. Just looks like an artist's rendition of a nice evening, and that is, again, a set of nebula that will ultimately grow new baby stars. So you know the closest star to us is about 4 light years away, named Proxima Centauri. Say again? Well, there's what's that? So it's called Proxima Centauri, but there is a star, and then there's the Alpha Centauri, the galaxy and whatnot. But what I wanted to point out here is, while this looks like it might have been a close-up of the star, it's actually an internet dupe. It's actually a slice of chorizo. So the reason I wanted to share that is because there's so much fake stuff out on the internet. You really have to be careful with what you're seeing and make sure you're getting it from a reputable source, which I may sound sarcastic, but you got to look at the government sources to get the truth. But so this is just a reminder to you folks to be careful what's out there. I got a few more quickies. I'm sure I can get through this in the next 5-10 minutes. Okay, well, you wanted some questions too. So Jupiter, did you know it had a ring? You guys know too much. Okay, so we're learning it's got a ring. It's also got auroras on the north and south poles that you can see in infrared. Saturn, this is a picture from Hubble. Beautiful picture. When we look at it from the infrared, you can't even see the main planet because the methane actually blocks a lot of the light itself. It absorbs that. Here's a picture of Uranus from Hubble. And from James Webb, what did we learn? Uranus has a whole bunch of rings also that you cannot see in the visible light. And right, we kind of knew it was tilted, but now you can really see based on the rings. Here's a flyby of Voyager 2, Neptune, which is way out there. Very nice close-up. This is what Hubble could see of it. And guess what? Every single planet with Jupiter on has rings around it that we may or may not have known. So this is the last chart. And I found this one to be another interesting one, another galactic oddity. But we're always wondering, is there life out there? Well, they're asking too. There's actually a galaxy in the shape of a question mark asking, are you guys out there? So just something fun. I thought I'd end on that. And we'll call it a day. We might have 2 minutes for questions then. No, it's orbiting with the Earth. It's staying with the Earth, but orbiting the sun. So it stays that 1,000,000 miles away, and it just is always 1,000,000 miles on the opposite side of the hours to collect something that it's looking at. Because just looking at objects far away, there's such dim, very few photons. They have to stare at it for 12 hours to get enough light in to actually get a reasonable image. Yeah, it can change position. So at any point, it's just not allowed to look towards the sun, but it can stare at something and hold it there accurately for 12 hours and then go look at something else. Does that make sense? Question? A majority of them have. They have seen a few outside of the galaxy, and again, it's that kind of thing where you got to see enough of the star to tell whether it's wobbling or something. So yes, but there have been very few, but most of them have been inside of our galaxy, which is still huge. You get an extra point for paying attention. That is true. That's correct. It's not likely looking like that at all anymore, correct? Potentially, yes, exactly. I think we have several billion years yet to worry about that. So you can sleep well tonight. We've got time. A couple more, I guess. 5 billion. So, okay. Okay. So we have 1 billion until what? Until we start melting. Okay. Well, please, don't anyone lose sleep over this presentation tonight. Okay. Well, thank you.